Okay, so today I'm going to have a look at the cube roots of unity. That's the cube root, 3 cube roots of 1. So I'm going to have a look at a few different ways of doing this. So the first way I'm going to have a look at doing it is just simply by factorizing. So if we take, for example, x cubed is equal to 1, we want to find a cube root of 1, so we just solve this, in other words. So what I'm going to do is bring the 1 over to the other side. So first thing I'm going to do is just have a look at x cubed minus 1 is equal to 0. Now the 1 here is just 1 cubed, and we know we can factorize x cubed minus 1 cubed. It's the difference of 2 cubes. So that's going to be x minus 1, x squared here. Then we multiply these two terms, which is going to be 1 times x, which is x, and then square the 1, so that's 1 squared, which is 1. So I know all of this is equal to 0, so if I look at the first one, for example, here I've got x minus 1 equal to 0, which gives me x is equal to 1. So this is my first root of 1, my first cubed root of 1. So what about the others then? I should have another 2, and they're contained within this expression here. So let's have a look at that. We have x squared plus x plus 1 equal to 0. Now if we try to factorize this, we're going to run into problems. So what I'm going to have to do is use the quadratic formula. Now, the quadratic formula is just x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Now in this particular case here, a is 1, b is also 1, and c is also 1. So I'll just plug those in here and see what happens. We have minus b, so it's minus 1, plus or minus the square root of b squared, so that's 1 squared, minus 4 times a times c, and that's all over twice a, which is 1. Okay, so let's finish this off. So we have minus 1 plus or minus the square root of something over 2. Now 1 squared is 1, and then this becomes minus 4 here, so 1 minus 4 is minus 3. So we have a negative number in our square root symbol here, so let's try and sort that out. Okay, so we've got minus 1 plus or minus the square root of minus 3. So I'm going to rewrite minus 3 as minus 1 times 3. Again, that's all over 2. So we have minus 1 plus or minus the square root of minus 1 times the square root of 3 divided by 2. So that's just going to become minus 1 plus or minus, now the square root of minus 1 is I, and we have our square root 3 here. So I'll put the I over on this side, divided by 2. So these are our two roots here. So our two roots are actually complex roots. Okay, so let's write down the 3 roots that we found. The 3 roots are x is equal to 1, x is equal to minus a half plus root 3 over 2i, and x is equal to minus a half minus the square root of 3 over 2i. Okay, so there are 3 roots. Now we can find these using Dumas Theorem, so let's have a look at doing that. So we have 1, which can be written as 1 plus 0i in rectangular form. So let's say z cubed is equal to 1 plus 0i, and we want the cubed root of 1 plus 0i, so it's going to be raised to the power of 1/3. So how do we do this? Well, we need to take 1 plus 0i and convert it into polar form. So let's do that. So if we have a look here at our Argand diagram here, we have our real axis here and our imaginary axis up along here. And where does 1 plus 0i lie on that? Well, it's going to be out here on the real axis, out here somewhere. So this is our 1 plus 0i out here. So it's out along here. Now we can see the distance out along here is 1. So in other words, the modulus of 1 plus 0i is going to be just 1. So we have r here is just going to be 1. So that's the modulus of 1 plus 0i, if you like. We've got to find the angle as well, the argument. Well, the argument is easy enough to find. It's just going to be 0 here. So in other words, we can write 1 plus 0i in polar form, which is going to be 1 times the cos of 0 plus I sine 0. That's our polar form here, and this is our rectangular form here. So let's just rewrite this here in polar form. So we have z is going to be equal to, actually what I'm going to do is write it in general polar form, because remember this angle here out as far as here we can is 0. This angle here is 0. We can go around once, that's 0 plus 2 pi. We can go around again, so that's 0 plus 4 pi plus 6 pi and so on. So let's just rewrite this in general polar form. So what we've got is cos of 0 plus 2n pi plus I sine 0 plus 2n pi. Now I've left out the 1 here, but what we need to do here is raise all of this to the power of 1/3. I'm just rewriting this line here, but writing 1 plus 0i in polar form. Okay, so let's just work with this. So really we have z here is just cos 1/3 of the angle. Remember, this is Dumas Theorem. We've got to bring the 1/3 down here, multiply it by the angle. So it's going to be 2n pi over 3 plus I sine 2n pi over 3. This is what we're going to work with now. So let's start then. We're going to start with n equal to 0 first. So if n is equal to 0 here, we're just going to end up with 0 over 3, which is 0. So we just simply end up with our first root here is going to be the cos of 0 plus I sine of 0, because this is going to be 0 as well. So the cos of 0, well, the cos of 0 is just 1. And the sine of 0, is 0. So 0 times I is 0. So this here is our first root of 1. Okay, so let's move on and look at the next n. So now we want to look at n is equal to 1. So if n is equal to 1 here, what we'll end up with is z2 is equal to the cosine of 2 pi over 3 plus I sine 2 pi over 3. Now if we have a look at that, we have here our imaginary axis again and our real axis out here, and we have our original complex number out here. This was 1 plus 0i out here. Now we are looking at an argument now of 2 pi over 3. So we're starting here. So 2 pi over 3 is 120 degrees. So it's going to be in this quadrant here. So let's say it's here. So this here is 2 pi over 3. 2 pi over 3. Now our reference angle then, if you like, is this angle here, which is pi over 3. Because this, remember, this is pi out as far as here, which is 3 pi over 3. We've gone out here 2 pi over 3, so we just have another 1 pi over 3 to go. So our reference angle is pi over 3. So here we have z2 is equal to the cos of pi over 3. Well, the cos of pi over 3, which is the cos of 60 degrees, is the cos of pi over 3 is half. And in the second quadrant, remember we have A, S, T, C here. All three are positive in the first quadrant. Only sine is positive in the second quadrant. Tan is positive in the third quadrant. Cosine is positive in the fourth quadrant. So the cosine of pi over 3 is a half. It's going to be negative because it's in the second quadrant. So we're looking at minus a half here. Plus well, the sine of 2 pi over 3 is the sine of pi over 3, which is root 3 over 2. So let me just put that first, root 3 over 2 I, and it's positive because sine is positive in the second quadrant. So this here is our second root of 1. We just have one more to go. So let's have a look at n is equal to 2. So n is equal to 2. And we have z3 now is going to be equal to the cosine of what? Well, let's have a look at our original expression here. We have cos 2n pi. So if n is 2 here, 2 2's are 4, so we end up with the cos of 4 pi over 3, and the same here. So the cosine of 4 pi over 3 now is what we need to look at. So it's 4 pi over 3 plus I sine 4 pi over 3. So where is 4 pi over 3? Let's just go back to our diagram over here again. Well, 4 pi over 3 is bigger than pi, so it's going to be down here. It's actually going to be the conjugate, the complex conjugate of this one up here. So this is 4 pi over 3 here. Now you can write this as minus 2 pi over 3 as well, so maybe we'll do that. So in other words, this angle here is minus 2 pi over 3, or all the way around here would be 4 pi over 3. So let's just rewrite this as Z3 even is equal to the cosine of minus 2 pi over 3 plus I sine minus 2 pi over 3. Now again, our reference angle here is just pi over 3. This is pi over 3 here. So we need to find the sine and the cos of pi over 3 and then deal with the sines. So let's have a look at that. So the cosine of, well, actually if you look at the cosine here, the cosine of minus 2 pi over 3, we're talking about the third quadrant here, so it's going to be negative because tan is positive in the third quadrant, so our answer is going to be negative here. So we need the cos of pi over 3, which we found out before is a half, so it's going to be minus a half. Also here we need to find the sine of pi over 3. So the sine of pi over 3, our reference angle, is root 3 over 2, but again it's in the third quadrant, so it's going to be negative root 3 over 2 I, and this is our third root of 1. Okay, so that's it. Using two different methods we found the same roots. So let's just have a look at, I'll just mention another method that you can use. We won't go through it in detail. It's effectively the same kind of thing. Okay, so you can use the exponential form as well if you like. So that's just z is equal to e, well it's or e to the power of I theta. It's the same kind of thing. Or is the modulus, and this is your angle up here. You'll effectively get the same, you will get the same results. So I won't go through that as well, but this is just the exponential form of your complex number. Let's just have a look at our three solutions again, and we'll just look at the properties of these three solutions. So our three solutions for x, if you like, were 1 minus a half plus root 3 over 2i, and then minus a half minus root 3 over 2i. So let's have a look at the properties of these roots. So the first one here that I'm going to look at is where we multiply one of these roots by itself. In other words, we square this root, we should get this one here, and vice versa. So if I call this one here omega, this one here will be omega squared, and vice versa. So let's just have a look at that and see, does it work? Let's take minus a half plus root 3 over 2i. I'm going to multiply that by itself. Minus a half plus root 3 over 2i. Okay, so if we multiply these two together, we'll get minus a half times minus a half, that's plus a quarter. So these two here then, minus times plus is minus root 3 over 4i. These two here, the same thing again, minus root 3 over 4I, and then finally these two here, plus root 3 times root 3 is 3 over 2 is 4, and then you've got I squared here. So let's tidy that up. We've got a quarter here. I'm just going to do this one here because this is actually a real number, because I squared is -1, and -1 times 3/4 is -3/4. These two here, we've got minus root 3 over 4, minus root 3 over 4, that's minus 2 root 3 over 4I. So that'll give us here minus a half, and minus 2 into 4 is 2, so we end up with root 3 over 2I. So when we square this one here, we get this here. And you can also do it the other way around. If you square this, you will get this. I'll leave that for you to do, but it's fairly straightforward to do. If we take either of these complex roots and square them, we'll get the other complex number. Okay, so let's have a look at the second property that I want to have a look at then, and that's just if you multiply these three together, you should get 1. That might be fairly intuitive, but let's have a look at it anyway. So if we take omega times omega squared times 1, that'll give us 1. That's really because in this particular case that's omega to the power of 1. Add the two powers here, you get omega cubed times 1. That should be equal to 1. Omega cubed is just going to be equal to 1. That's because omega is the cube root of 1, so if you cube a cube root, you'll get 1. So again, we can prove that. Let's just have a look at doing that. So let's take 1. Let's multiply that by minus a half plus root 3 over 2 times minus a half minus root 3 over 2. I should put an I in here as well. And that should give us 1. Let's just multiply that out and see what happens. So, well, 1 times anything is going to be the anything, so I'll just leave this one out. Let's just multiply these two here. So I got minus a half times minus a half, which is plus a quarter. Minus times minus is plus root 3 over 4I. That's these two. Now let's do these two here, so that'll give us minus root 3 over 4I. And then finally these two here, so that's plus times minus minus root 3 times root 3, 3 over 4I squared. That should be equal to 1. So let's see. We have plus root 3 over 4I minus root 3 over 4I here. Here we've got a quarter. And here we've got an I squared, which is minus 1, which means this should be plus 3/4 then, and that's equal to 1. And you can see that that is the case. 3/4 plus a quarter, 1 is equal to 1, so that's perfect. So when we multiply our three roots together, we do get 1. That's the second property. So let's have a look at the third property then that I want to have a look at, and that's just that if we take omega cubed being equal to 1, we can just split this up into omega times omega squared is equal to 1, because we can just add the indices here. So that would just simply mean that omega is equal to 1 over omega squared, or omega squared is equal to 1 over omega. In other words, the complex roots, two complex roots, are inverses of each other. So let's take an example then. Let's take, for example, the inverse of one of our roots. Let's say minus a half plus root 3 over 2I. So I want to just convert this to rectangular form, a plus bi. So let's just multiply it by its conjugate over itself. Conjugate of the denominator, I should say, over itself. So it's minus a half minus root 3 over 2I divided by a half minus root 3 over 2I. What we're doing is just simply taking that fraction there and we're multiplying it by 1 in the form of the conjugate of this denominator over itself. So what happens if we multiply all this out? Well, we'll get on the top minus a half minus root 3 over 2I. On the bottom, if we multiply it all out, we get a quarter, and then this one plus root 3 over 4. These two here, sorry, that's root 3 over 4I. These two here then is going to be minus root 3 over 4i, and then finally these two here, minus 3 over 4i squared. Now if we have a look at this, on the top we just have minus a half minus root 3 over 2i, and then on the bottom these two here will cancel, and here we have an I squared which is just minus 1, so just this will change to a plus 3/4. So we have a quarter plus 3/4 which is 1, so this is all over 1, so we finish up with 1 over 2 minus root 3 over 2i. Now this here is what we get when we did this here, when we did the inverse of, or the reciprocal of, one of our roots. So the root we picked was minus a half plus root 3 over 2i, and we ended up with minus a half minus root 3 over 2i, which is the other root. So that just confirms what we said here. Okay, so the fourth property then we're going to look at is just simply adding the three roots, and we should find that we get 0. So let's have a look at that. One of our roots, minus a half plus root 3 over 2i, we're going to add that to the other one, which was minus, put them in brackets here actually, it doesn't really matter, but minus a half minus root 3 over 2i, and then we're adding 1, and we should get 0 out here. So let's just take away the brackets here. So we've got minus a half plus root 3 over 2i minus a half minus root 3 over 2i plus 1 equal to 0. You can see here that we have a plus root 3 over 2i, a minus root 3 over 2i. These two here will give us minus 1. Here we've got a plus 1, so we get 0 is equal to 0. So this does hold up for our three roots. You can also think of them as just simply three vectors. We have our Argand diagram again. We have one of them here. So this was one of them out as far as here. If we just write that as a vector here, if we just represent that as a vector. The other one was up here. Again, that's a vector of the same length. This is 1, this is 1. And the other one was down here, also 1, all equidistant from each other, and they actually form an equilateral triangle here. So the three vectors will look something like this. If we put them together, we end up back at 0 again here, and our three roots will add to give 0 as well. So that's really it for this particular video. Talk to you again in the next video.